In this video lesson, we are going to cover the mathematics behind the phase changes, specifically that of melting, freezing, vaporization, and condensation. When we talk about the mathematics behind these phase changes, there are two terms to be aware of: heat of fusion and heat of vaporization. First of all, I'd like you to notice the signs that correspond. First of all, you'll notice each one has a delta H. This actually has the scientific term change of enthalpy, but for right now you can just think of it as heat. And then there's two terms, fusion, which has the subscript FUS, and vaporization, which has the subscript VAP. We're used to vaporization being going from the liquid to the gas phase, but fusion is a term you might not be familiar with. Fusion is just another way of saying melting, and so when you see fusion, think of melting. Alright, so let's define what these two terms mean. First of all, heat of fusion. Heat of fusion is defined as how much energy is needed to melt 1 mole of a substance. Notice that it's always in relation to 1 mole. So for example, water has the heat of fusion of 6.01 kilojoules per mole. What that means is if you had 1 mole of water, it would take 6.01 kilojoules to melt that 1 mole of water. The other term, heat of vaporization, is similar. This is how much energy is needed to vaporize 1 mole of a substance. So for example, we're looking at water again. Water has a heat of vaporization of 40.67 kilojoules per mole, meaning that if you had that 1 mole of water and wished to vaporize it, it would take 40.67 kilojoules. First of all, note that these are for the actual phase changes themselves. So when you're at the point of melting, which means 0 degrees Celsius, that's when it will take 6.01 kilojoules to take it from solid to liquid water, and 40.67 kilojoules to take it from liquid to gas. Notice that the value for heat of vaporization is larger than that of fusion. The heat of fusion is always going to be less than the heat of vaporization. The reason for that is because when you're taking something from a solid to a liquid or melting it, you're just weakening the forces. But when you're vaporizing a substance or taking it from liquid to gas, you're actually breaking the forces. You're not just weakening them. So that takes more energy. Now notice these are for endothermic processes, meaning you have to put heat in. You have to add heat to melt something or vaporize something. But if you wanted to do the reverse of those processes, meaning if you wanted to freeze something or condense something, you would just take the same amount of energy but reverse the sign. Meaning if I wanted to freeze 1 mole of water, I would have to remove 6.01 kilojoules per mole. And if I wanted to condense 1 mole of water, I would have to remove 40.67 kilojoules per mole. In other words, I just have to reverse the sign. Right here is a table of common heats of fusion and heats of vaporization for some common substances. Notice that we have water, benzene, and ammonia. Those are some common ones. Obviously, there's a lot more substances, but this is going to be the table that we use to do the practice problems on the next slide. We're going to need to know specifically the values for benzene, which is 9.95 and 30.8, and then water as well, which is going to be 6.01 and that 40.67 value. So let's do some practice problems. All right, the first one says, if you have 15.0 grams of ice at 0 degrees Celsius, how much energy is required to melt it? So notice you have the substance already at its melting point. There we go, at its melting point. So now you just have to go through the process of melting. This setup is going to be basically dimensional analysis. We're going to take a look at the value we're currently given, which is 15.0 grams, and we're going to try to use conversion factors to get it to the unit we want, which is units of energy. So the first thing I'm going to do, just like I do with every dimensional analysis problem, is I'm going to write out what my given value is, which is the 15.0 grams of ice, which ice is just solid water. All right. Now, I'm in grams, and I want to get to units of energy, which is kilojoules. There isn't a direct conversion to get from grams to kilojoules. But what we can do is we can go from grams to moles, which is using our molar mass. And then once we're in grams and now into moles, we can then use our heat of either fusion or vaporization, depending on which one the problem's asking for, to get us into energy. So let's go ahead and do that setup. First, we need to get from grams to moles. So what I'm going to do is I'm going to divide my value of 15.0, I'm going to divide that by the molar mass. Grams of water goes on the bottom, and then moles of water goes on the top. That way the grams cancel out. For every 1 mole of water, it's going to have a molar mass of 18.02. So my grams cancels out, and now I'm in moles. So I've done the first conversion. The second conversion, like I said, is where we go from moles to kilojoules, which is where our heat of vaporization or heat of fusion comes in. So we have to look at what process is happening. Are we melting something, vaporizing? What are we doing? The question is, we are melting. Okay, so we have to put energy in, and specifically we have to melt, which means we're going to use the heat of fusion. So I'm going to put moles of H2O on the bottom, and kilojoules is going to go on top. And this conversion factor right here, this is your heat of vaporization, or excuse me, your heat of fusion. So let me write that down here. So yeah, so once again, this is going to be your delta H fusion for water. So if you were to look back at that chart that we saw in the previous slide and recall what that was, the heat of fusion for water was for every 1 mole of water you had, it would take 6.01 kilojoules of energy to melt. So the moles cancels out, and now we're in kilojoules. So let's go ahead and calculate that. My answer with the appropriate number of significant figures is 5.00 kilojoules of energy. Okay, let's go ahead and take a look at the second one. Second one says, if 2.45 kilojoules of energy are released when benzene is condensed, how many grams of benzene do you have? So now we're going the opposite direction. We are given the amount of kilojoules, and we're asked to go to grams. Once again, you have to go through moles first before you can get to grams. So let's go ahead and write down what we're starting with. 2.45 kilojoules of energy. Now notice the wording in the problem. The wording in the problem says 2.45 kilojoules of energy are released. So that word released indicates that it's a negative 2.45 kilojoules. All right, so now we set it up where kilojoules is on the bottom and moles is on the top. And specifically, it's moles of benzene, which is C6H6. All right, so now what I'm going to do is I'm going to recall what my value was looking back at that chart. But we need to know, what heat are we using? Is it heat of vaporization or heat of fusion? The phase change that we're dealing with is condensation. Well, there wasn't a heat of condensation, was there? But we have to think, what's the opposite of condensation? The opposite of condensation is vaporization. And so we need to figure out what the heat of vaporization was for benzene. When I look back at the chart, it was 30.8 kilojoules of energy for every 1 mole. Now this is 30.8 kilojoules of energy needed to vaporize. We don't want to vaporize, we want to condense. So that means 30.8 kilojoules needs to be released. So I'm going to put a negative sign there. The kilojoules cancels out, and now I'm in moles. The last step is simply just to do the molar mass. We have moles of C6H6 on the bottom, and we have grams of C6H6 on top. All right, so now I'm going to fill this in with the molar mass for benzene. So there's my molar mass. The moles will cancel out, and now I'm ready to calculate to get my number of grams. And there's my answer, 6.21 grams of benzene.